So here we are back in Unit 5, which is all analytical trigonometry. So thinking about trig in a different way. This is going to use things that we've thought about before in the past with our basics of trig functions, but really looking in a very different way. So this lesson is going to be all about verifying trig identities. So I want to teach you what that means. So what does it mean to verify an identity? I want to teach you about the basic identities that you know most of, and then how to actually verify an identity. As we do this, we have our target, which just says I can verify trig identities. That is what we're aiming for. And why are we doing this? So these identities are going to help us when we solve trig equations, but also this entire lesson, we'll spend several days on this, is really good for practicing thinking logically through a process. So this is something that, warning, it's not easy, because you have to really think about it. You have to be willing to, try and maybe go back and start again. So this is going to be really good practice thinking through that kind of process. So let's start out with, what does it mean to verify an identity? This says it means we are showing that one side of the identity can be simplified so that it is identical to the other side. So we are basically proving that something is true. All right, so verifying an identity, we're going to be proving that something is true. So what I want to do is go through the sheet that hopefully you printed on the fundamental trig identities. This says AKA identities you need to know. So these are going to be things that we're going to be using all throughout. The better you know them, the easier these will be. So let's start out with our reciprocal identities. So notice in this first section, these are things that you know. You had to know these facts to find exact values. You had to know these facts to graph trig functions. So you should feel pretty comfortable with the fact that sine and cosecant are reciprocals. So all this says is rewrite sine as 1 over cosecant, or rewrite cosecant as 1 over sine, using the fact that they're reciprocals, saying, hey, you're allowed to write them in a different way. Second set, again, we know cosine and secant are reciprocals, so you could write cosine as 1 over secant, secant as 1 over cosine. Same thing with tangent and cotangent, using the fact that they're reciprocals. All right, so these are really just, hey, you can rewrite any function as 1 over its reciprocal. Then we have our quotient identities. So our quotient identities, we saw these pretty early on with trig. This says that tangent of x is equal to sine of x over cosine of x. What does that mean? That means you can rewrite tangent as sine over cosine, or you can simplify sine over cosine to just tangent. Looking at, how do these things fit together? Since then, cotangent is the reciprocal of that. Cotangent can be written as cosine over sine. I'm thinking about, does this actually make sense? How is that true? Think about Sir-Sixertix. Right? So if we say tangent is the y over the x, is that really equal to the sine, which is y over r, over the cosine, which is x over r? And we can show it. Y over r times r over x simplifies. The r's cancel out to y over x. So that's just showing you that it does work based on things that we know how to deal with. How I remember this in practice, like which one is which, cotangent has cosine on top. So to me, that's the easy way to remember that. So there are reciprocal identities that really you already know, but just saying that, hey, like we can use these to rewrite something. And then our quotient identities, where tangent is sine over cosine, cotangent is cosine over sine. Next up, we have our Pythagorean identities. So I think this looks overwhelming because right now I'm showing you a list of 9 different equations. What I want you to focus on is this top one. All right, we saw this equation already in action this year. We said that sine squared of anything plus cosine squared of the same thing always gives you 1. We talked about how you can draw a triangle and how sine is the y value and cosine is the x value. So Pythagorean theorem holds true. So that's our basic identity. If you can remember that, then you can find all the other ones. So look at how these three are all the same identity, just written in different ways. So here's what this says. If you're in a problem and you see sine squared plus cosine squared, you can call that just 1. If you in a problem see 1 minus cosine squared, you can replace that with sine squared. If you see cosine squared, you can rewrite it as 1 minus sine squared. You can use either direction on these. So if you saw the 1 in a problem and you needed to, you could rewrite the 1 as sine squared plus cosine squared. So I think, those three are pretty nice because we have our basic one we've dealt with before and then the 2 variations. Let me show you how you can derive these 2 and not actually have to do any memorizing. All right, so if we start out with our basic identity, sine squared plus cosine squared is 1. We pick one of these 2 functions to divide through by. I'll pick sine. So I'm going to divide through by sine squared. And look at what happens. Sine squared over sine squared is 1. Cosine squared over sine squared, we just said cosine over sine is cotangent. They're squared, so it's squared. 1 over sine, reciprocal of sine is cosecant. It's squared, so it's squared. 1 plus cotangent squared equals cosecant squared. There's that identity right there. Okay? So you can find it if you need to based on your basic identity. We can do the same thing here. Start with your basic. Divide through by the other function. So here's cosine squared. And let's see what we get. Sine over cosine is tangent. They're squared, so it's squared. Cosine over cosine is just 1. 1 over cosine is secant. It's squared, so it's squared. That is this identity here. So if you're in a problem and you start seeing squareds and 1s, you're thinking about your Pythagorean identities. You have to know there's really no way around knowing sine squared plus cosine squared is 1, but then you can find the other ones that you need. So those are Pythagorean. And then the last ones are going to be our even or odd identities. So what this says, if you look here at the first column, we have an odd function. So sine is classified as an odd function because if you put a negative into sine, a negative angle, you actually end up with a negative answer or the opposite of your original answer. Same thing for tangent. But notice when you get to cosine and its reciprocal secant, that when you plug in a negative, nothing happens. All right, let me show you why that makes sense. Because it's one thing to see, okay, fine, that's true. But another thing to understand why. So let's talk about pi over 4. All right, here's the angle pi over 4. Here's the angle negative pi over 4. All right, so pi over 4, I'm a 1, 1, root 2 triangle. So if I think about sine of pi over 4 is 1 over root 2, which is root 2 over 2. Sine of negative pi over 4, the y over the r, gives negative root 2 over 2. Look at how sine of the negative angle gives negative sine of the angle. Sine of the negative angle gives negative sine of the angle. You compare the two and you've switched the sign. So look at the difference between cosine. What makes cosine even? Cosine of pi over 4 is root 2 over 2. Your x over your r is root 2 over 2. Cosine of negative pi over 4, the x over the r still gives you positive root 2 over 2. So even though you put the negative angle in, you kept the same value. That's what it's saying. And then if I did tangent, we would go back and we would get a positive and a negative. So that's all it's saying. So if you have a negative inside of a cosine function, really it can go away. If you have a negative inside of a sine or a tangent function, it can come out front because it will end up making the whole value negative. All right, so those are all of the fundamental identities. So here are some tips. You definitely want to write these down, the tips and the methods, because these are what we'll use in the next video. It's going to be all about examples. So a couple of tips. Memorizing the identities, really knowing those are going to be, that's going to be really helpful for you. Second thing says start with the more complicated side and transform it. So typically I want to start with the side that looks harder, and that's the one that I want to change around. If it seems like what you're doing is not working, don't be afraid to start over. These are things that you should be using pencil or a whiteboard marker, something that you can erase, because you might try something and you might be doing really good math, but it doesn't get you to where you need to go. So you have to start over, and you can't be afraid to do that. All right. If I'm driving and I get lost, I don't just keep going in that same direction forever. I turn around and I figure it out. And that's going to be the same idea here. You have to be willing to turn around and figure it out. Going to be really picky here to show every single step. You have to show exactly what you're doing. That's going to be really, really key here. And then notice that last thing says you can only change one side. We don't want to end up with kind of a hot mess that we're dealing with. So you're going to keep one side as if it's written in stone, and you're going to have to deal just with the other side. We have 5 methods that we can use that we use while we're doing this. First one that works sometimes is just to change everything in a problem in terms of sine and cosine. So that's an option, that we could change everything in a problem to sine or cosine. Another option is to factor. So sometimes we will see that we could factor. Another thing we can try is separating fractions. So if we had something like x plus 3 over 3, I could write that as x over 3 plus 3 over 3, which is x over 3 plus 1. So the fact that you're allowed to separate a fraction is a thing. Combining fractions with a common denominator, really like going backwards, right? If you start with 2 terms, you can combine them with a common denominator. And then last one is multiplying by a conjugate. Remember what conjugate means. If I have this 5 over 2 plus root 3, how do I simplify that when we're in radicals? I use the conjugate. 2 minus root 3 is the conjugate. So that's what I would use. I do it because the conjugate makes really good things happen. All right. When you FOIL them out together, they cancel out. Not completely, but with the radical term. So here I would get 4 minus 3, which would just be a 1 in the denominator. So that would be friendly. All right. So those are the background thoughts. At this point, you have no idea what I'm talking about. You have not yet verified an identity. So join me in the second video, and I will actually show you how to verify an identity.